So we're very pleased to have for our second talk Alkistis Elliott-Graves, now of the University of Bielefeld, and she's going to talk to us on the title, What are General Models About? Thank you.
Thank you. So I'm very glad to be here. Thanks for inviting me. Thanks to everyone for coming. So my talk today is about general models, and general models are kind of relevant for this workshop because they are one of the sort of most common highly idealized model. They're used extensively in lots of sciences, and there's also a lot that's been written about them in philosophical discourse. Now, what I want to do today is take a closer look at how we understand generality. And my claim is going to be that there's actually two very different ways in which we can interpret the notion of generality in general models, and that has kind of sort of important implications. Both of these ways of understanding generality have sort of their own set of epistemic issues. So that's the first claim that I'm going to make. And then the second claim that I'm going to make is going to be a little bit stronger. And I'm going to say that actually confusing these two or failing to distinguish between these two kinds of generality and general models is going to be dangerous because it leads to sort of bad practice in science. Okay. So I'll illustrate this difference by talking about sort of two exemplars of the kinds of generality that I'm interested in. Now on the left, I think it's on the left for everyone, you have logistic growth. This is a model that describes how populations grow when they're only constrained by themselves and the resources in the environment. So you have a population that grows and its growth rate grows, and then all the resources start getting used up and then it stops growing. Now, it's used extensively in ecology, despite being very, very old and very, very simple. And it still is being used in ecology, not as much as it used to, but it is still being used. So this is going to exemplify the first type of generality that I'm talking about, and that's why it has G1 next to it. On the right is Schelling's model of residential segregation. And that is going to be the model that exemplifies the second type of generality. So Schelling's model is meant to show how neighborhoods can become segregated, even though residents only have sort of mild preferences of being around neighbors who are like them. So this is a typical net logo version of the model. And here about 30%, so each person wants 30% of people to be like them in their neighborhood. If you run the model just with this mild preference, sort of not outright discrimination, then you get segregated neighborhoods. I'm not going to go through these models very much in much more detail because I'm assuming that everyone knows about them quite well already. One thing I want to say about the Schelling model is that the important sort of insight about it is that it shows how sort of individual level behaviors can lead to large scale macro effects. That was one of the reasons that it was very important. Okay, so a little bit about the generality here. We'll go back to the logistic growth model. So in what sense is this model general? Well, it's general in the standard sense. It's general in the sense that it applies to many systems in the world. And not only, I mean, it's not just me saying this, the people who invented it intended it to be used for many systems in the world. These are actually some of the original drawings, and they are sort of graphs, they are drawings, and there's about, I don't know if there's 20 or 30 of them, but there's definitely more than 10 in the various papers and books. And these are all logistic curves applied to various different types of populations. Here I've got New York and Connecticut, I think, or New Jersey, and Drosophila in a lab. There's been Germany, Japan, human populations, and then various other animal populations. So from the very beginning, This model was general in the sense that it was intended to apply to many systems in the world. Okay, so a little bit of context for this kind of generality. I picked Levins here for a number of reasons that I'm not going to go into. His is a very good illustration. He's not the first or the last person to talk about it, but his sort of view kind of exemplifies a lot of what both scientists and philosophers think about when they think about generality in this way. So Levins's point is that in complex systems, you can't do everything. So modelers have to choose what desiderata they're going to maximize in their models. Generality is one of three main desiderata, the other two being realism and precision. For Levins, generality means applying to many real-world systems. Realism here refers to how many causal factors that are present in the world are captured in your model, and precision refers to how finely specified the model's results are. So here, this kind of generality, this notion of generality is one of three desiderata. In any particular model, you can only maximize 2 out of 3. That gives you 3 strategies for model building and 3 corresponding types of models. Out of interest, the logistic growth model is a type 1 model in this view because it maximizes generality and precision, but is low on realism. So many of the idealizations that happen in this kind of model are on the realism side. So what that means is that a lot of factors that we know exist in the world are left out, and some of them are idealized. I'm not going to talk about that very much. Okay, so the main issue, or at least a very important issue with this kind of generality, is that there's an ambiguity between applying widely and applying well. So let me talk about this in a little bit more detail. So when we're saying that a model is general, do we mean that how well does it need to apply to each system in order to count as applying, right? So a lot of people have written about this. For my purposes, I'm just going to say that applying well here equates to predictive accuracy. So it doesn't matter. I'm not going to care about what it takes, how we can, how models are made to apply better or worse to various systems. I'm just going to look at the outcome of the model. So in other sense, how do we test whether a model applies well? How do we know that a model has applied well? Well, its predictions are accurate. I'm just going to take that for granted. Okay, so why is this a problem? Well, the problem is that when you generalize, you focus on lots of commonalities between systems, right? So you focus on the core factors that give rise to the phenomenon that you care about, and you leave out all of the weird, unique, idiosyncratic factors that are also going on in various systems, right? If you figure out the right causal factors across all of these systems, then you get a model that applies to all of them. Now, the problem, though, is that sometimes a lot of these idiosyncratic factors can actually be relevant. So the more general, the more widely a model applies, the fewer factors it's going to have, because there's fewer factors that are common across different systems, and the less predictive accuracy it's going to have. And there's a reason for this. This is not just random. It's because in a lot of these systems, especially in complex heterogeneous systems like the ones in ecology, social sciences, you name it, the problem is not that you're not capturing causal factors that are relevant. You are capturing them, but there are additional factors that are going to mess up your predictions. Okay, so just an illustration of this. The exponential growth model is even simpler, even more general than the logistic growth model. in the sense that it has even more factors and it applies more widely because it applies to every single population that the logistic growth model applies to, and the ones that don't have density dependence. The problem, though, is that if you actually look at it in terms of applying well, it only applies really well to bacteria in labs for a very short period of time. So it is general in one sense, but less general in this sense of applying well. And of course, the more complex you go, the fewer models that the model applies to generally, but the better it applies to those specific ones that have those causal factors. So for example, if you adapt your model to include abiotic factors, they tend to work much better for plant populations, but then tend to work much worse for animal populations, and vice versa. Okay. Now, moving on to the second type of model. Here the model is general, again, but I want to claim that it's general in a very, very different way, right? And we can see, I mean, it's not just Schilling himself didn't go to various cities in the United States, look at how segregation works, and then abstract away and come up with a model that describes all of these populations by focusing on what was common across various actual cases. No, what he did was he was actually on a plane. Emre Aydınonet's paper, he has this wonderful interview of Schilling, and he tells you how he came up with it. He's trying to figure out how to tell his students about this segregation thing, and he just sort of thinks about it and then makes the model. And importantly, this is really important, he never tried to apply it to any actual city in the world, right? So this notion of generality, if it is generality at all, that's giving away the punchline, at best is a very different notion of generality. Why? Well, because it's not meant to apply to many systems in the world. It's meant to apply to an abstract phenomenon or idea. Okay, so the main issue with these kinds of models that are sort of about these abstract phenomena or ideas is that we kind of need to give an extra story about why they're valuable. In the first case, it's pretty obvious why they're valuable. Having a general model allows you to sort of subsume a bunch of different phenomena under a particular explanation. You find out the actual causal factors that are relevant. You can use it to make predictions, explanations, all of that is all very well. But what happens here? How are these models valuable? Well, there's a lot that's been written about that. And the main two ideas are how possibly explanations and this idea of expanding the causal mechanism schemes. So how possibly explanations are not explanations about how segregation comes about, but how segregation could come about. And that is useful because it can help you figure out things about segregation, even if that's not what's actually going on in the world. So the idea here is that you can get information about the real world, but indirectly. So you can do this in a number of different ways. You can reduce the number of unconceived alternative mechanisms. That's what a lot of my former colleagues at Helsinki have been writing about. So, and that gives you sort of greater confidence that our models are kind of capturing something generally by figuring out that there's something that actually could work. And this can be quite important for interventions in the actual world in an indirect way, because so the idea is, even if you could remove, for example, institutionalized segregation, you could still worry that shelling mechanisms could still persist despite removing these other causes, and then that could lead to segregation persisting. Okay, so an important thing to note is that my distinction between G1 and G2 types of models is not identical to Michael Weisberg's and John Matthewson's distinction between A and P generality. Now, what they mean by A and P generality, A generality is actual generality, which is exactly what I'm talking about when I'm talking about G1 models. The difference is in P generality. So P generality for them is possible generality. So it's how many possible systems does the model apply to. Now, as I have on the slide, you might think that there's not much going on here. There's not enough of a distinction because G1 models have A generality, because A generality is applying to many actual systems in the world. And also G2 models have P generality in the sense that they can also apply to many possible systems in the world. Now, I don't have anything against this distinction. It's just orthogonal to what I'm talking about. There's two reasons for this. First, G1 models can also have P generality. So just like that distinction doesn't map on to the distinction that I'm making. The second is that P generality is not, it kind of misses the point about what is good when what is valuable about G2 models, in the sense that there is some value in applying to many possible systems, but I think the real value of G2 models is that they are about these abstract phenomena, these abstract ideas. I'm happy to talk about this more later. I expect that people are going to worry about this. Reviewer number 1 has already. Okay, so now if we're going to talk about what models are about, then one really good way to do this is to figure out what their target systems are. Now, target systems are, according to me and some other people, what models are about. But that, of course, doesn't give us enough information because no one can actually agree on what target systems are. So I'm going to leave that aside, what target systems are generally. Do read my paper that has finally come out if you feel like subjecting yourself to something like that. But I'll just focus on targets of general models. And to do that, I'm going to look at Michael Weisberg's account, because that is, to my knowledge, the most extensive and comprehensive account of general models and their targets in the literature. And it happens to be interestingly wrong too. So for Weisberg, general models have generalized targets, which are intersections, i.e. they're abstractions over the actual targets that share the features. So they're not parts of the real world, they're one level removed from the real world, and they're not, and they're abstract. So he has this great passage where he looks at the example of sexual reproduction. So models of sexual as opposed to asexual reproduction. Consider the target of a generalized model. Such a target is by its very nature more abstract than any specific target. A generalized model of sexual reproduction isn't supposed to be about kangaroo sex or fungi sex, but about sex itself. So then he continues, this is why Crow's model of the origin of sexual reproduction has no detail about any specific species in it, but nothing in the world actually looks like sex in general. There is kangaroo sex, Tasmanian devil sex, human sex, but not sex in general. So sex in general is an abstraction over the more specific kinds of sex. Right. So for Weisberg, general models have generalized targets because they're not interested in, so the people using these general models are not interested in learning about sex in all of these cases, but they're actually interested in only in the idea of the general abstract notion of sex. Okay, so what I'm going to claim is that this account is a little bit strange in the sense that it kind of manages to misrepresent both kinds of generality, both kinds of models. It doesn't get right either of the two completely. Now, first of all, it gets G1 targets wrong and the role of these models completely wrong. because the logistic growth model, for example, as we've shown very explicitly, was meant to be about all of these populations. So it's not like it's not about kangaroo sex or Tasmanian devil sex, blah, blah, blah. It's about all of those individually, every single one. So it's about kangaroo sex and Tasmanian devil sex and human sex. And in this case, growth is about Drosophila growth and human growth and ant growth, etc. So there's something really odd about this kind of phrasing. So in other words, the G1 models are not just used for minimalist idealization or possible explanations. They are used in order to understand what's going on in the actual world. Okay, so how does it misrepresent G2 models? So it misrepresents how these models actually come about. Now, Schelling, as I said, didn't go around the United States looking at how segregation worked. He didn't even sort of conduct an experiment with his students to see if segregation could work like that in the actual world. No, it was a complete top-down way of thinking about creating the model. There's no intersection in the target systems in the way that Schelling actually constructed his model. And again, Weisberg's account misrepresents the point of these models. They're not about, the point is not that they have common features that are shared across various different systems. That's irrelevant. The value of the model is in terms of whether it generates a how possibly explanation. Okay, so to sum up this part of the talk, my claim is that actually we should, we should definitely keep these two notions apart. I would very much like to restrict the notion of generality to G1 models. I think that's really what we're talking about when we're talking about generality. And if we're going to talk about G2 models, we should at best call them generic, right? So the targets of these models are also generic. So the first are general and the second are generic. And I think that kind of captures the distinction, the relevant distinction. Okay. So far for the sort of theoretical stuff, but who actually cares? Well, I think that this sort of failing to distinguish between these two things can have implications for actual scientific practice. And I'm going to now outline two problems which I think are not entirely created by this confusion, but definitely exacerbated by it. So the first is the problem of overgeneralization. This is a problem of G1 models, right? Because obviously if you're a G2 model, you don't need to apply well to any actual system. You just need to apply, and you don't even need to apply widely. You could apply widely to various possible systems. The point is that if you're a G1 model, then actually applying well is quite problematic. Now, when you're doing applied science, I have this nasty picture of dead salmon, is because of some conservation, I can't remember which one it was, but there's some conservation effort that went massively wrong and this kind of thing happened. So like we're in the real world, we have real problems, we can't afford to make mistakes. It's not just not having your paper published, lots of things can go wrong. Now, what does this have to do with overgeneralization? Well, I believe that this sort of failing to distinguish between G1 and G2 models kind of makes us have way too high expectations about how general models, G1 models ought to be, right? Because if you are used to Schelling type models that could explain segregation everywhere, right? But no one's actually tested if they have, then you kind of also expect your G1 models to apply really, really widely. And just in case you think that this is not a real problem, these are just some examples of theories in ecology that have been sort of touted as like the really, like the explanation, the theories to end all other theories in ecology, that was going to revolutionize everything. They were going to apply across the board to all sorts of different types of ecological systems, and then they failed, right? So it's not like it doesn't happen, it happens a lot. So yes, I think we should definitely kind of rein in our expectations of how widely G1 models are going to apply. Now, the second danger occurs with G2 models, and that is when people smuggle in how possibly explanations and kind of make them end up looking like how actually explanations. And I'm picking on Michael Weisberg here just because he makes it really easy. He doesn't actually say this super explicitly that this is what he's doing, but in his book, he has these two pictures side by side and he says, look, you could get a how actually explanation from a how possibly explanation by checking out, by seeing how well the model relates to how similar it is to an actual target. In this case, he says that you have 75% segregation in both the net logo and actual Philadelphia. So we could infer, he's saying, that this mechanism that led to segregation in this target was the same as the one in the in Schelling. Now, here's a problem with that. We haven't actually really checked whether the Schelling mechanism causes segregation in the way that Schelling said in the world, as far as I know. In fact, there are a bunch of, oh no, come back. There are quite a few sociologists and lawyers who have spent a lot of time looking at actual segregation in the States. And they have come up with an alternative actual explanation of how cities in the States have become segregated, right? So I think that it's really kind of dangerous to keep on thinking of the Schelling model as one that could give you, that is giving you a sort of interesting possible explanation. No, I don't want to say that, that's too strong. It is giving you a possible explanation, but we need to be really, really sure that we're not investing too much time and effort into looking at possible models of explanation. Whereas what we should be doing is actually checking the actual methods and mechanisms for segregation. So these people claim that actually Schelling type mechanisms are insufficient on their own to bring about segregation, and only through these top level kind of backed by law kind of mechanisms can you get the kind of segregation that we see. So these people are kind of making an implicit claim that the Schelling mechanisms are actually couldn't possibly bring about the kind of segregation that we see. So what I think we should do is really kind of, as philosophers, we should really kind of look into that and kind of actually go and test whether the Schelling mechanism can give you the kind of segregation that we see in the United States. And if we don't want to do that, that's all fine and good, but we should be really absolutely 100,000% extra careful to not ever say anything that could make anyone possibly think that we might be implying that a Schelling type mechanism is going to give you segregation in actual cities. And with that, I'm going to end. Thank you very much. And yeah, questions? I should probably